last talk is also from someone from UMKC, Kameswara Mantha, and his topic is major merging important at early cosmic times, data theory tension, selection bias, and future prospects.
Awesome. Again, I'm Kameswara, and today I will be talking more about mergers. We have heard a lot of merger talks today, which is really interesting, and I think it's safe to say that you will agree that major merging or merging in general is really important when it comes to galaxy evolution. So this work, so I'm going to talk about what I did, what I'm doing, and what I'll do with Dr. Madalyn E and in collaboration with the Candles team. So let's look at the three main points that I'm going to talk about. I'm going to talk about major merger rates that I measured. I'm going to talk about some selection biases and some really interesting results. And AI. I'm going to talk about the marriage between AI and astrophysics. Awesome. Let's look at merger rates. Now, merger rates are calculated really using this simple formula right here, where merger rate is given by R, and you measure using I'm using a specific method called as a close pair method, where I look at galaxies that are in close pair, in close proximity to each other, and you measure a close pair fraction, and you assume a number for this and a number for this time scale during which they're observed as close pairs, and that's called an observability time scale, which I'll come back to later. It's really these two play a really important role in this calculation actually. But here are my assumptions, and here are my results. So the key punchline, you can find it always here on top of my slides. So the key punchline is that we find that the major merger rate increases from a redshift of 0 anchored using a Sloan low redshift point that we measured, and then it increases up to a redshift of 1-ish, and then it actually declines towards, we find that it declines up to a redshift of 3. Okay, that's the key punchline from this plot that I showed you. Now let's analyze it a little bit more closely. So if you compare it to the known observations, it agrees up to a redshift of 1 to 1.5 within the error bars. And when you compare it to the model predictions, here are two model predictions from collaborators Vicente Rodriguez Gomez 15 paper and Hopkins 2010 paper. You can clearly see that the close pair method is it's a direct method that, of measuring galaxy merger rate, because you don't have morphological based biases. It's just close pairs. If they're bound, they're likely merging. But this direct method somehow is showing a different result than the prediction from the simulations, sometimes by a factor of 5, which is really surprising. So we need to understand the discrepancy on what's happening. So let's look closely at the equation. Okay, why am I wrong? So I can be wrong here, I can be wrong here, and I can be wrong here, or a combination of those things. Okay. The first step in trying to answer this, and also notice that I introduced this redshift dependency, which is a really important step because most of the cases they are not assumed as evolving. It's always a constant number, which I think should change in the upcoming studies that people do. So the first step is I'm asking, is there a selection bias? Okay, let's look at this. And one of the important criteria that we use to select major merging is to select those close pairs with a nearly close stellar masses, or stellar mass ratio of 1:4. However, owing to we know that galaxies are more gas rich at high redshifts, and star production or star formation rate is directly proportional to the cold gas content of the galaxies. So I said, okay, let's test something that was initially speculated in many of the studies, that if you use baryonic mass, the total baryonic mass to select galaxy mergers, is there something, does it agree with stellar mass ratio criteria, or does something else happen? So I use gas masses from Popping et al. 2015 for a subset of Candles galaxies, and produce this first ever result showing that we are actually missing galaxy mergers or galaxy major mergers. actually both minor and major mergers. If you are selecting based on stellar mass ratio, if you ignore the cold gas mass of a galaxy, you are missing major mergers. The punchline is that previously everyone has used the stellar mass ratio criteria to select galaxy mergers. Those are underestimated according to this result right here. Okay, and it not only this, it also has a lot of it can explain a lot of other things, including the triggering of star formation and our AGN activity, if you think about it, because you are missing those mergers that have actual gas in them, and you are only selecting gas poor in some sense, and it might explain some of the studies that find lack of AGN activity or even sometimes lack of elevated star formation activity, which is a really interesting result to follow up on. Awesome. Let's try a different method now, because I don't want to bias myself to a single method. Another method is to use tidal features to identify galaxy mergers. Tidal features are more direct. You can look at them and you can just say, well, that's merger. Now, which is a visual classification. So if I ask anyone in this room without even showing anything, is this merging? You'll be like, yeah, that's merging because I see a tidal feature. So visual classification is a straightforward method that is usually employed to pick out these tidal features. Okay, but you can do this on 500 galaxies or 1,000 galaxies. If you have 5 grad students, you can probably do on like 5,000 galaxies. But it's a lot of time and maybe a lot of subjectivity that's going in. And I think at some point we have to sort of either limit it or completely able to stop it and make it automated, which is where I'm going to talk about my AI. Thanks to the speaker earlier, explained most of the architecture and the stuff about the neural networks. So I'm going to use a similar model, which are called as convolutional neural networks. And here's an example on how important they are and how they grew in their importance in different fields. They have tremendous uses, including like you can train it to say a joke even, and you can ask for basic object recognition and for cyber security. You'll be surprised to see its uses. For example, here I posed 2 questions. I randomly downloaded two images from the internet and I asked it what it is, and it predicts what it is. So it has a lot of promise when it comes to image-based analysis. Okay, so what I did is I'm going to design a network that is going to learn how to detect tidal features based on expert classifications. Visual classifications are important. I'm going to use them. So my preliminary pipeline, what it's going to do is going to use 4 images from 2 different wavelength bands, each a galaxy, original galaxy image, and its tidal residual from galaxy, simultaneously convolving and trying to extract important features that correspond to tidal structure. And here's my model right here, and I'm just going to outline it. This part is responsible for extracting your information that corresponds to the features, and that maps in its hyperspace on, okay, this corresponds to tidal feature, and it learns, basically like a brain mapping inside the brain. Now finally it changes into interclassification. Awesome, let's look at it. So the punchline is CNN works. Preliminary, even without doing any sort of fancy modifications to it, you can see here I have 2 examples. One is just the left side is normal galaxy and the right side is the tidal feature, the tidal residual from Galfred. And WIS stands for the visual classifications, what the visual classification said, true. And AI predicts it's true, and it has a chance of 99.6% of being true as a merger. Chance of being a merger is the chance here. Now, similar example, you take a galaxy, visual classification said false, AI says false, and pretty low chance of being a merger. So we actually turned this into a Hubble proposal and submitted it yesterday. Hopefully it goes through. Okay, let's look at what I'm going to do in the future. So I come back to these guys over here, actually all 3 of them. Now, there are 2 things we need to do. We actually have to split the method to understand method-dependent calibrations, because I'm using closed pair method initially, and you have to know how this changes using simulations. I'm going to use semi-analytic models that were produced by 3 independent groups in Candle's collaboration actually. And I'm trying to constrain this and this using closed pair method, and applying closed pair method onto semi-analytic models. Now similarly, I'm going to use the synthetic images from one of our collaborators, Snyder, and we are going to apply the CNN that I showed you on the synthetic images, and also the and some of the visual classification that we do on those images, in trying to get at these values. These are really, in my opinion, these values are really important, and their evolution is also very important. They'll provide key insights into the disagreement that we see between the models and the observations. Because this calibration has never been done before, and this will tell you in many other side projects on how frequent do you see a tidal feature, or how frequently can you miss them, which is very good important information when you're trying to say something about AGM fractions or star formation fraction based on these specific features on specific selections. Awesome. So some possible side projects that I'm working on. If you are interested in any of the machine learning stuff and also anything in this talk, basically, feel free to contact me. I'm more than happy to collaborate. I love machine learning. Other projects that I'm trying to work on is automatic visual classification instead of just tidal classification, and some like photometric that are also based on just image-based photometry independent photometric redshifts estimations that the machine will give you. For example, here the red line here is the spec Z of a galaxy. You give it an image, a multi-band image packed into like five different wavelength bands. You ask what redshift it is. The probability peaks exactly on top of spec Z. So which is something I would it's in-house, and we are trying to like sort of develop it like an in-house code and probably leave it to some other grad students. So I did this as a project for the Sci-Fi 2017 Python conference. My 3 main conclusions: merger rates are declining up to a redshift of 3. Selection biases: we are missing major mergers if you are selecting using stellar mass ratios. AI, machine learning is awesome.